I've got two fairly straightforward examples for you in this wonderful, exciting video. First one is an LC circuit, and the next one is an LRC circuit. So here we go. We have a 1200 picofarad capacitor. We charge it up with 500 volts of DC power. Then we disconnect it from the power supply and connect it to a 75 millihenry inductor, and we see what happens. We're going to get some electromagnetic oscillations, and we're going to analyze a bunch of quantities. So the initial charge on the capacitor, for this case the inductor isn't even hooked up yet, so we could ignore it and we can just use Q equals CV. Now I'm going to use Q naught because that's the notation we're going to be using. So C is 1200, pico is 10 to the negative 12th, and then we multiply that by the 500 volts, and we get an initial charge of 6 times 10 to the negative 7th coulombs. Okay, for part B, we want to know the maximum current. So this is once the inductor is hooked up. Maximum current is given by omega Q naught. Omega is the square root of 1 over LC times Q naught. So square root of 1 over 75 millihenries is 0.075 henries multiplied by 1200. I'll just write pico here and remind myself to type 10 to the negative 12th when I put it in the calculator. And then we multiply that by Q naught, so 6 times 10 to the negative 7th. And this works out to be 0.063 amps, or 63 milliamps. Part C, we want to find the frequency and the period. Frequency is related to the angular frequency, this omega, by a factor of 2 pi, so we just do omega over 2 pi. We've already got omega, that's this thing up here, so we take that guy, divide by 2 pi, works out to be quite a large frequency, 16,776 hertz, or inverse seconds. The period is just the inverse of the frequency, and that works out to be 6.0 times 10 to the negative 5th seconds for one cycle. The last part D here, we want to know the total energy, which is given by Q naught squared over 2C. Q naught, we know, 6 times 10 to the negative 7th. Quantity squared divided by 2 times this 1200 pico coulombs and picofarads, and this works out to be a nice 1.5 times 10 to the negative 4th joules. Alright, on to an LRC circuit. Here we have some different values of stuff. It showed that it will oscillate, so what I'm going to do is I'm going to calculate 4L over R squared C and compare that to 1. So this is going to be 4, my L, where did I go, 40 millihenries, so that is 0.04. R squared, that's just 3 squared, and my capacitance, 4.8 microfarads. So this works out to be 3703.7, which is greater than 1, and greater than 1 means that you will have underdamped, so QED, I guess. QED, it will oscillate. Alright, determine the frequency. We're going to plug into that different frequency equation. Actually, we just had an equation for omega, but to get to frequency, we just multiply by, or divide by a factor of 2 pi. And then this guy here was our omega, R squared over 4 L squared. I won't write all the numbers plugging in. This works out to be 363.2 hertz. Okay, part C, the time required for the charge amplitude to drop to half its initial value. So essentially that decaying exponential part in the equation has to equal 0.5. So we can set that decaying exponential, negative RT over 2L equal to 0.5. And then we just have to solve for t, so we're going to get RT over 2L, negative sign there, is equal to the natural log of 0.5. And just solve this guy for t. T equals a negative 2L over R times the natural log of 0.5, and that works out to be 0.018 seconds. Okay, the last part here, we want to know the value of R that will make the circuit non-oscillating. So essentially we want R squared to equal 4L over C, because when that is the case, you are critically damped, and anything equal to or greater than that, we consider it to be not oscillating. But we need to find R, so it's going to equal the square root of 4L over C. Plug in your numbers, and you get 182.6 ohms. And that's it. See you next time.